Separate chaining in hash table. Separate chaining is a collision resolution technique used in hash tables. How do you resolve collision using separate chaining? Here, you maintain a linked list corresponding to each bucket in the hash table. What is a bucket? In the previous lecture, when we showed you the hash table, we showed you like an array. That is, each of the memory points or each of the indices of the hash table, we showed as if it can only contain one element. But in case of separate chaining hash table, you can have a lot of entries inside the same index. So because of that, you call each of them as buckets. Why buckets? Because inside single bucket, you can put in a lot of input data. Because of that, you call each of these as buckets. And inside the bucket, you are maintaining a linked list. Let us see how this is done. So for each of these indices, you will be maintaining separate linked lists like this. So whichever element maps to these particular indices, all of them can be simply added to this linked list. So there will be no collisions. Why? The whole concept of collision is based on the fact that you have an entry to which if an additional entrant comes in, you can't accommodate it there. That is the whole problem in case of collision. But here you are saying that whatever be the number of entries, you will take all of them inside the same index because you will have a separate linked list. You just have to add the new entry into the linked list, which means there is no concept of collision at all now because you can't collide. All the entries will be simply put into the same index. So in this case, what is the procedure? You will have a hash function, same as the previous concept of hash table that we learned. You will use this hash function in order to find the right index. How do you find index? Any entry will generally be in key value pairs. What is this? The key is what you generally use in order to compute the hash value. So you put the key into the hash function and you will generate corresponding hash value. In the hash map, you will be storing hash map or hash table. Hash table, you will be storing this key value pair as the entry. So corresponding to the key, you will have a value. Whenever you want to search this, you will search for the key. So you will put the key into the hash function. You will generate the hash value. Corresponding index, whatever it be in the hash table, you will come and search for the key. Whenever you get the key, you will see what is the value stored corresponding to that key. This is how you do search in a hash table. So in case of this separate chaining hash table, what will be the procedure for inserting any element? For insertion, you have to initially compute the hash value. Once you compute the hash value, what can you do? You have to find the corresponding index and put the key value pair into that index. So this is the procedure for insertion. If this is the procedure, then what is the time complexity of insertion? If this is the procedure, in best case, what can happen? In best case, let us say you found some particular index here. What is the best case? That index has no elements, which means you can add as the first element in the linked list. In this case, it will take order of 1 time complexity. This is the best case. In case you are in the worst case, then what can happen? In case of worst case, your time complexity can go to order of n. How is it order of n? It can be order of n because what if you have a very large hash table, let us say, but all the input values that you used, all of them somehow maps to the same index. Let us say you computed hash value for all the different keys you got and all the hash values turned out to be of the same index. What happens then? Every single entry you are bringing in, everything will be added as a chain here, as a linked list. What happens then? If you want to search, again, if you want to insert itself, it will take order of n because let us say this is the present condition. you added one more element. So presently there are n elements already present and you added one more element. The new element, if you have to add it, you have to first get into this index and then get into the end of the linked list, because in the linked list you generally add at the end of it. So you have to go till the end of the linked list. So this will take order of n time. You can only travel through a linked list linearly. So this is where order of n, which is the worst case time for insertion, comes in. But I told you hash table generally doesn't take order of n time. The reason is here you have to consider average case. What is the average case here? Average case is order of alpha, where alpha is your load factor. In the previous lecture, we learned about load factor. What is the load factor? It is the number of keys present divided by number of buckets. Let us say n by m, where m is the total number of buckets you have here, total number of buckets, and n is the total number of keys, different keys that you want to insert, that is n. Then what happens to this alpha? Alpha is generally, if you consider uniform key distribution, this alpha will be a constant value. So in that case, your average case time complexity, that will become a constant. So it will be somewhere near to order of 1, almost a constant. So this is what happens when you have uniform distribution of data. What is uniform distribution of data? You are assuming that if you have 10 buckets and a total of 100 input elements, you are assuming that each of the buckets will have 10 elements. See, even if it is not 10, if it is somewhere near to this, let us say this is having 8, this is having 12, this is having 9, and so on, you still call it uniform. So if you can somehow maintain uniform distribution of keys in the input, then your load factor will be a constant. So if load factor is not very high, then your time complexity of insertion, which is order of alpha, will also be a low value. So this is how you generally say that a hash table, separate chaining hash table, can do in constant time. But the worst case is order of n for insertion. Okay. Next thing is, how do you search for element? Searching also follows a very similar procedure. Whenever you get a key, you have to search for the key, not the value. Okay. You have key value pair inserted. You will always search for key. So how will you search? You will put key into the hash function. You will get a hash value. Once you get the hash value, you will check in the hash table. Then you have to search linearly in the linked list. So this is again the time consuming process. So again, everything is almost same as the insert case. Your best case time complexity is order of 1. Worst case time complexity is order of n. And average case time complexity is order of alpha. So again, here you are assuming uniform distribution, and in case this alpha is not large, then you are doing very good with the time complexity. Deletion, again the same process. Compute hash value, traverse the linked list, locate the key, and then remove the key value pair. This is the process in deletion. So the time complexities will again be the same for deletion as well. The next question is about space complexity. What is the total space complexity of separate chaining hash table? Space complexity will be, see, one point of space usage is for this storage of indices. So for this indices, you will store it as much as the number of elements in the as the total number of entries already present in the hash table, that is number of buckets. So what is the number of buckets? M is the number of your buckets. Here we used M as the number of buckets. If you have a total of M buckets available in the hash table, your space complexity should be order of M because of those M buckets. Plus you have one more factor. The other factor is the linked list that you are adding. So for each of the element that you are inputting, each of the keys n, you will have one linked list, one new node in the linked list, which means order of n space is required in order to add n different keys into this hash table. So the total space complexity is whichever is greater, among order of m or order of n, that is space complexity is order of n plus m, right? This is the space complexity. One more thing, what can be the value of load factor here? In the previous lecture, we said if it gets close to 1, it is almost full. But in this case, even if it is close to 1, there is no concept of full here because you are having linked list in each of the bucket. Because of that, you would say that for efficient operations, it's better if your load factor is less than 1. If it is less than 1, it is negligible and hence your time complexity will be constant. Otherwise, if it happens, then n is much greater than m. That is, you are having a lot of keys and very less buckets. In this case, performance of your hash table will degrade. So a good hash function, first thing is whenever you are using a hash function, if you are having a good hash function, it should minimize collisions. It should uniformly distribute the data. But if the case is that the data points you have, the keys you have is much greater than the total number of buckets, then automatically the number of entries in each bucket will increase. So if you are considering that your load factor is low, in that case, hash table can provide very good time complexity, and space complexity is anyway order of n plus m.